Okay, so we've looked at expected value now, and we've looked at sort of what a discrete distribution entails, specifically, again, countable variables. And now we're going to look at a specific kind, a common kind of a discrete probability distribution. It's called the binomial distribution, so a binomial random variable. And these variables are based on something called the Bernoulli process, famous mathematician Jacob Bernoulli. And in this process, we're looking at two possible outcomes, specifically a success, which we'll denote with the probability of lowercase p, or a failure, the probability of 1 minus p. So if we only have two possible outcomes, it makes sense that the failure would be 1 minus p because there are only two possible outcomes, either p or not p, the complement of p. And just note that in this process, it's the same probabilities for each trial. So the probability of success is always going to be consistent. They're not necessarily going to be equal to each other, but the success is always going to be the same in every single circumstance. In general, the binomial distribution, the binomial random variables, it's the number of successes achieved in n trials. So if we think of rolling a die, so rolling a six-sided die, if I wanted to find the probability of rolling a 5 in 10 trials, that's what we would look at, where a success would be the probability of rolling a 5 versus not rolling a 5. And again, it's looking at distributions with all possible values associated with x. It's countable, so we can easily write it out. But beyond just dice rolling and coin flipping, this actually can serve a very practical purpose. So let's say that a manager at a sports stadium concession stand determines through experience that 85% of customers use a credit card to make a purchase. If 3 customers are in line, I want to create a binomial distribution showing the number of customers who use credit cards. So one way to really tackle this problem is through a visual. So what we can do is create something called a probability tree that outlines every possible outcome that could occur of those 3 customers. Specifically, we can look at the likelihood of someone having a card versus the likelihood of someone paying without a card. So we can see here, again, the probability of getting a card in this case we can see is a 0.85, and the probability of not getting a card would be a 0.15. So the first customer can do one of two things, either pay with or without a card. Now, based on that, the next customer could do the same thing, could either pay with or without a card. If we look at this first part, we say that the probability of paying with a card is 0.85, and then the probability of paying with the card on the second customer is also 0.85. Similar with that other situation. So the first customer pays with a card, but then the second customer pays without a card. And we notice that the probabilities are not changing. And this then goes on to the first, the second, and then the third customers, and we can see that there are really 8 total outcomes of what could happen. So if I just go down one of these tracks, so let's say the first person pays with no card, second person pays with a card, and the third person pays with no card, I can just follow those tracks, and the probability of that happening is the product of those 3 probabilities. Now, what's nice about this is that from this particular circumstance, we can then lay out, the probabilities of each one of these things occurring. So let's say the probability of all 3 people play with a card. That would be this one circumstance, 1, 2, 3, the very top rows here. The very top rows here, we have 1, then 2, then 3. Oops. And the probability of all those happening is 0.85 times 0.85 times 0.85, or 0.61. So the probability that all 3 people pay with a card is 0.61. The outcome of 2 people paying for a card, so that could be card on the first, card on the second, then no card on the third, or card on the first, no card on the second, card on the third. That occurs 3 times. The probability of each one of those is 0.85 times 0.85, 2 people who paid with a card, times 1 person who didn't. And then to figure out the probability of all 3 of those occurring at the same time, it's just 3 times 0.11. So each one of them is 0.11 likely. So 3 times 0.11 is 0.33. So roughly 33% of the time, there's going to be two people who pay with a card and one who doesn't. Following suit, one person who paid only with a card, so that means two did not. The likelihood of one of those situations happening is just 0.02. So if I do that 3 times, there are 3 different occurrences in this tree diagram. I can multiply 0.02 times 3. So the likelihood of only one person and 3 of them paying with a card is roughly 6%, 0.06. And then no one paying with a card seems rather unlikely. It's roughly 0.3%. Now, a tree diagram can be an excellent visual, but I'm wondering if there's a shortcut for it, and there is. There's actually a very convenient formula that looks rather messy, but essentially does this process for us. So for a binomial random variable x, the binomial distribution, the probability of x successes in n Bernoulli trials, again, it's just showing that you can either be a success or a failure, is equal to this very ugly formula, but all this is the combination of n events, choosing x of them, and then we just take the probability, we raise it to the number of successes, and then 1 minus the probability, so the number of failures raised to the number of failures. An important thing to note here is that the probability, the 0 factorial, if I'm ever going to have a 0 factorial, that's just equal to 1 here. So these x values are going to change based on the number of successes that we have. And I think that this is this seems rather overwhelming, but it's actually doing exactly what we just did with our tree diagram. So let's show a specific example. Let's say I want to look at the probability that, all right, if I have an 85% likelihood that someone with a card, an 85% likelihood that someone with a card is going to happen. Let's say I want to determine the likelihood that all 3 people pay with a card, and I'll also determine the likelihood that 2 of the 3 people pay with a card. And I'm going to use this formula instead of the tree diagram. So in this case here, if I know that my x value is equal to 3, all 3 people are paying with the card here, all 3 are successes, I'm just going to plug in every one of these cases, well, n is still going to be equal to 3 because we're still looking at 3 total customers here. But the x value is equal to 3, so every time in my formula I had an x value, I'm going to plug it in, and I'm specifically going to use this equation over here on the right hand side, the n factorial one. So in this case here, I'm going to plug in a 3 for every one of my x values. So those x values are occurring, we'll use the pen, x values are occurring here and here. We're seeing that the likelihood of a success of using a card was 0.85, again raised to the 3rd power, because all 3 of them in this case are using it. And then 1 minus the 0.85 is our 1.15 are not using a card here, 0.15. So that would be considered a failure in this case. And again, the x value comes up here, or the n minus x case. But what happens here is intuitively this should make a lot of sense. So this determines essentially the frequency that it occurred, the frequency of the successes, and it always happened. So that was only one success in particular. The 0.85 to the 3rd definitely made an appearance in my tree diagram, specifically if all 3 are using the card, so 0.85 to the 3rd power, that makes sense to occur here. And then these number of failures, there weren't any failures, all 3 of them are using cards, so the percent of failing, there were no failures in this case, so it's 0.85 to the 3rd times just 1. Anything raised to the 0 power is 1. So intuitively, this should match up with the tree diagram, and it in fact does, because 0.85 to the 3rd times 1 particular occurrence of that, and there were no failures, so we just multiply that by 1 because it's not changing. To even further this argument, if I look at, let's say, 2 of the 3 cards now, let's say 2 of the 3 cards, 2 of the 3 customers are going to pay with a card here. So now x is equal to 2. We see that in the formula, all the x values are changed to 2 alone. Specifically, the exponents were appropriate. And when I simplify, it makes sense that a lot of these numbers come out. So here we see if two customers are paying with a card, we see that 0.85 squared come up because those are the two customers who paid with the card. We see the one customer who didn't pay with the card come up. That's the 0.15 to the first. And we see the occurrence, this 3 out here, saying that that occurred 3 different times in my tree diagram. So that also makes sense. And you notice that that calculation ends up being the exact same that it was from the tree diagram that we saw right here in the second row. The likelihood of having 2 customers out of the 3 pay with a card, we took the frequency here and we multiplied it by the probability of one of those events occurring. That's exactly what we do in this case here. So we can use a tree diagram when it's appropriate, but I think that going to the formula is extremely beneficial. It makes our life a lot easier, especially if you're comfortable with factorials. And it lets us very quickly see, especially if I have a lot of trials. So if I have something like 10 trials, then it becomes much more arduous to do a tree diagram for it. In this case here with the formula, if I just determine what nx is and the success is, then I can just plug a lot of things in and I can quickly see the probabilities of maybe choosing all 3 who pay with a card or just 2 out of the 3, and it could have done the same thing with 1 and 0. So this concludes part 3, the binomial distribution, and we're going to finish the last video, the last section, with the Poisson distribution, which is another example of a discrete random variable in our sort of discussion of discrete random variables.